Today I'm breaking down how a DC generator actually works, in 3 steps: parts, process, and types. First, the parts. The hardware that makes the magic happen. The yoke, think of it like the sturdy outer frame. It holds everything together and gives the magnetic flux a low-resistance path. The magnetic field system, fixed poles with field windings or sometimes permanent magnets that create the magnetic field the conductors will cut through. The armature, a laminated steel core with copper conductors tucked into slots, and it's the thing that spins. That rotation is key. The commutator and brushes, a split copper ring on the rotor, and carbon brushes that ride on it. They're the secret sauce for turning what's born as AC into a smooth DC output. Now the process, the physics in motion. At the heart is Faraday's law. Move a conductor through a magnetic field, and you induce an EMF, basically a push on charges. Faster motion, stronger field, more conductors in series, bigger EMF. Here's how it plays out in a DC generator. 1. The field coils energize and build a magnetic field between the poles. 1. A prime mover, like a turbine, engine, or even a crank, spins the armature. Each conductor on that armature slices through magnetic field lines. 1. As those conductors cut the field, an EMF appears. It's maximum when the motion is perpendicular to the field and drops towards 0 when it's parallel. 1. Fleming's right-hand rule gives the current direction: thumb for motion, index for field, middle finger for induced current. As each conductor swings past 180 degrees, its local current flips. So inside the armature, it's naturally alternating. That's where the commutator earns its keep. The split ring swaps the connection to the external circuit at the exact moments the internal current reverses. So even though the armature EMF is alternating, the output at the brushes stays unidirectional, DC flowing to your load. It's like a mechanical rectifier, making sure the outside world sees a steady push in one direction. Last piece, types, the ways we feed those field windings. Separately excited, the field gets its DC from an independent source, like a battery or a small supply. Super controllable field strength, great for precise output regulation. Self-excited, the generator bootstraps its own field from its output. 3 flavors: shunt, field in parallel with the armature, stable voltage at light to moderate loads; series, field in series with the load, voltage rises with load current, punchy but less stable; compound, a mix of shunt and series. You can tune it to stay steady, flat compound, or to compensate voltage drop under load, over compound. So that's the DC generator: sturdy yoke, strong field, spinning armature, and a clever commutator turning raw alternating induction into clean DC. If you remember Faraday for the why, Fleming for the which way, and the commutator for the make it DC, you've got the whole story. If you want a deeper dive, I can break down real-world losses, armature reaction, brush drop, and how to size conductors for a follow-up.